see this one box. Oh, and
Well, shoot.
you remember
23rd.
Yep. No, what would you eat on best way?
Okay.
Unlimited budget.
All right, here we go.
Buttered lobster. Mashed
Okay,
potatoes with
recall.
shot. You better not bake this
Okay,
thing.
so no. All right, so we have an example. Hey guys, we gotta get going.
For seven,
Short period today. We're gonna go to church together. We're gonna renege ourselves. And those of you that have to leave are just going to leave when they have to leave. Okay, so factored form, there we go. What do we notice about it? We're gonna have a hole. And where is the hole going to be? I'm on my 111 notes. Notes 1.11. I'm on example 1. Already got it factored. So where's my hole going to be? It's gonna be at -2, yep. And then how will I find my whiteboard? Remember, the hole is a point, so I need to put it somewhere. Plug it in, so that'll be -4 over 3. Alright, everybody okay with that? Now, notice the x plus 5 did not cancel out, which means it's going to be a vertical asymptote. And we're going to write it as an equation always, x equals -5. Okay? What's our domain? For this particular problem, what's our domain? Everything except -5 and -2, right? That's our domain. So here's my number line. I can't be -5 and I can't be -2 because those would both give me a 0 in the denominator, right? So what is my domain? Negative infinity to -5. -5 to -2, and -2 to infinity. That's my domain. Everybody okay with that? Yeah? Alright, let's try example 3, same thing. So let's factor it. How does the top factor? -4 plus 3? Perfect. Now on the bottom, be careful, what are you going to do first? Take out an x. And when I take that out, I'm going to have x squared plus x minus 20. So that's going to factor as +5 minus 4. Perfect. So once again, we're going to have a hole. Would you agree?
Yep.
And where will that hole be? At +4. $7.36. It isn't, but is that what you got? Alright, so write the equation in factored form, get it, okay. This one I am going to graph, so I'm not going in order, obviously. I wasn't paying attention. But I'm going to go ahead and start graphing it, so I'm going to put my hole at 4, 736. And this is what we're graphing now, right? Because we took our hole out. So tell me what else I know about my picture. It may not be in the order it is here, but it doesn't matter. What else do I know?
Vertical asymptote at -5.
Vertical asymptote at 0 and at -5. Okay, perfect. What else can you tell me?
Horizontal asymptote at 0.
Horizontal asymptote at 0, and how do I know that? Because the bottom power is bigger than the top, and that always means 0 for your horizontal asymptote. identify zeros. Now, remember, zeros are when this thing equals 0. The only way that a fraction can equal 0 is if its numerator is 0. So what makes your numerator 0?
Negative 3.
Negative 3. Do I have a y-intercept? No, no, no. Because what do I have on my y-axis?
Asymptote.
An asymptote. Alright, so let's see. I got my zeros, I got my holes, vertical, horizontal. Okay, what's my domain? What's my domain? Negative infinity to negative 5. Negative 5 to 0. 0 to, watch it, no.
Oh,
To 4. And then 4 to infinity. Remember, we're looking to find the domain of the original problem, right? And there are 3 breaks in the domain. So I'm talking about there are 3 values that x cannot be. So even though you found a y value there, remember that is open. All right, let's see if we can sketch it now. It says to use a graphing calculator to help us, but I think we can do this without the calculator. Let's see if we can, and then we'll, are all you people singing?
We're doing the Hail Mary.
I'm doing a Hail Mary.
Yeah, we're doing
Okay,
it.
perfect. All right. Okay, so let's see what we can figure out. Do we remember that we are never crossing either axis unless we've already identified a point, right?
Wait, are we coming back after the
Yep.
Oh.
So, over here, would you agree that I have to either have this or this over here? So I'm just going to check one point, like negative 6. And if I put in negative 6, it's like problem here. If I put in negative 6, I'm either going to get a positive or a negative output, right? And that's going to tell me what that looks like. So let's go ahead and put in negative 6. If I put in negative 6, I'm going to get a negative over a negative times a negative. What's happening over here? Would you agree it looks like that? I'm trying to do this without my calculator. All right, now, there are lots of things that could happen in here. Not lots, but could it be a parabola opening up or down, or some kind of squiggly, like a cubic function going either direction? I can tell really easily, because if I plug in negative 4 and negative 2, then I will know whether I'm above or below 0. Agreed? So here we go. Negative 4 would be negative, negative, positive. So over here, I'm positive. Does that make sense to everybody? Now I have a feeling what's going to happen over here, but let's double check it. Let's put in negative 2. If I put in negative 2, I am indeed going to be negative. So I get a shape that looks like that in there. You okay? And then what do you think's going to happen over here? You should know. What's going to happen over here? See, that's part of the curve. So doesn't this one look like this?
Isn't there a horizontal asymptote?
At 0.
Why can the cubic thing cross?
Well, we talked about that. Can anybody remember? What did we say about that?
Oh, they can cross through. They just get closer, like as you go left or right.
Okay, yeah, so maybe it was the other class we talked about this. Horizontal asymptotes are what? They're limits. End behavior asymptotes. Horizontal asymptotes, end behavior. And what does it mean for when we talk about end behavior? We talk about the limit as x approaches infinity or negative infinity, right? So where are these things really asymptotes? They're end behavior asymptotes. So they're really asymptotes out here. Now I drew it all the way across just because it's convenient to do that, but they're not really asymptotes in the middle. Horizontal asymptotes are asymptotes out there. They describe what the curve does as it heads off the page. The curve is doing all kinds of weird things in the middle. Okay, does that make sense? You can cross a horizontal. Eventually, it'll level off and approach. You will never cross a vertical because verticals are not end behavior. What are verticals? Undefined, right? And that's non-touchable. Okay? All right. Let's see what we got next here. Example 4, a graph is shown above. Could you write an equation for this? So it's going to be a rational function. And we're going to write an equation for this in factored form. So what are some things we know? We practiced this a little bit the other day. What are some things we know? We have a 0 at 3, so that means what? In my numerator, x minus 3. Because where do zeros come from? The numerator. All right, what else do I know?
There's a whole at 4.
I have a whole where x is 4, which means I have to have an x minus 4 in the top and the bottom. All right, what else do I know? A vertical asymptote at 2. A horizontal at -1. Now, how am I going to do that? Put a negative in, maybe right here. Because remember, when you multiply all this out, that would give you a negative x squared over a positive x squared. So that's going to give us that. Now, is there anything else I need to check? I got to check that the hole's in the right spot. So when I put in what am I putting in? 4? When I put in a 4, let's see, my reduced problem would look like this. Okay, when I put in a 4, I'm going to get -1 over 2. Does that look about right?
Yeah.
Looks perfect. Everybody good? All right, would you try number 5 on your own, you and your teammate? Try number 5 and see if you can come up with an equation there. Alright, what were your non-negotiables? What were the things that you stuck in there? X minus 1 on the top, and why did we stick in that? Because that's where we cross the x-axis. Perfect. Alright, what else did you stick in?
X minus 2 on top and bottom.
X minus 2 on the top and the bottom, because that's where we have a hole. Okay, what else? X minus 3 on the bottom, because that's where we have a vertical asymptote. And an X on the bottom, because we also have a vertical asymptote there. Is that good?
I put a negative.
Well, let's talk about that. Does this have a horizontal asymptote where it's supposed to? Yeah, because when you simplify, or even before you simplify, the power on top is going to be less than the power on the bottom, so you have that horizontal asymptote at 0. Now your final check is when you put in 2, you're supposed to get about 1/2. But if I put in 2 here, I'm gonna get 1 over 2 times -1. Right? So Olivia said, I put a -1 up here.
I put it in front of the bottom, but I don't.
Doesn't matter. Yeah, you can put it somewhere. Here's the deal, folks. Is that gonna change anything else about the picture? Is that gonna change any of the asymptotes or any of that? No, we have to be careful because putting a negative in can change your horizontal asymptote, but not when it's 0, right? It's not gonna change. And then that'll fix that, and that'll work. And that negative can be on top or bottom, it doesn't matter. Okay? All right. Recall that if the degree of the numerator is 1 greater than the degree of the denominator, then we have a slant asymptote. In other words, we have a linear end behavior asymptote. So let's look at the function that we've got here. I'm going to do some factoring. We okay with that? All right, so, let's see, do I have a hole? Yes, I do. Where's my hole? Where's my hole here? 2 comma what? 8/3. Perfect. Do I have a vertical asymptote still? Yep. Do I have a horizontal asymptote? Not horizontal, but I do have an end behavior asymptote to talk about. So we'll do that in a second. Do I have any x-intercepts or zeros? Have one at -2 and have another one at 0. And that point actually will also be my y-intercept then. He's having you do long division, which we'll do one. We'll do one where it's necessary, but it isn't necessary in this problem. So we're gonna go ahead and do synthetic division. We have x squared plus 2x divided by x plus 1. So to find the end behavior asymptote, we'll divide x plus 1 into x squared plus 2x. We did this the other day. You did it last year. So here we go. Remember, the curve will never touch its asymptote. So the equation is never going to be exactly the line. So this, we expect there to be a remainder and it doesn't impact us. That's what keeps the curve from touching the line.
Administrators, please excuse the interruption. All those involved in the rosary this morning are excused to head to the WAC. Thank you.
Okay. All right, so are you okay with that end behavior asymptote? Everybody okay? All right, in this we'll be on the long division, but as long as you've got a situation like this where you're dividing by a binomial like this, you can always do synthetic. And if you were graphing this one, which we're not, but if we were, he's already graphed it. If we were graphing it, remember, that's a line with a y-intercept at 1 and then a slope of 1. So your asymptote would look like that. All right, now we're going to do a long division problem. We're not gonna do that one. So we're gonna do example, well, let's talk about example 6. And then we'll talk about example 7. Example 7, I haven't done it yet, so I don't know if the factors or not, but let's look at example 6. Does example 6, can I do any kind of factoring? Do you think with this? No. I can do this with synthetic division if I don't mind fractions. Now we'll also do it with long division to practice, but remember what I said, as long as your denominator, the thing you're dividing by, is a linear binomial, in other words, it's 2x plus 1, x minus 3, 7x plus 5. As long as its degree is 1 and it's a binomial, I can use synthetic. However, to use synthetic division, do you remember your rule here about this? Do you remember what you have to do first if you're going to use synthetic division? This number that you're dividing by here, your divisor, that has to be a 1. So you can divide the whole shebang by 2. This is if you're going to do it with synthetic. So you really have 3x squared plus 1/2 x plus 5 halves divided by x plus 1/2. So if you don't mind fractions, you can do this with synthetic division. Personally, I avoid long division at all costs. I hate it. But we'll go through that too, and you'll just pick your favorite way. If I do it synthetically, then what am I going to put out here in the box? Remember, this is what I'm now dividing. So what am I going to put out here? Negative 1/2. So 3, 1/2, and 5 halves. So negative 3 halves. That'll give me 1. And I really don't care what happens over here because remember the remainder is of no significance when I'm doing an end behavior asymptote. So what will be my end behavior asymptote for this problem? Y equals 3x plus 1.
How is it 1?
It should be negative 1, shouldn't it? Thanks. I got so excited because it was a whole number. Is that okay? Now, let's run through it long division in case you decide that's more than you want to take on. If you do long division, then you don't need to worry about that. You can just go ahead and divide like regular. I mean, you don't have to reduce anything or change any of the numbers in the problem. And if you're going to divide 2x into 6x squared, That goes in 3x times. And then we'll take 3x times 2x and 3x times 1. And then we'll subtract, just like we do with regular division. Subtract. Bring down the next number, just as if you were doing it with regular numbers, like digits. Now 2x goes into negative 2x, negative 1 time. Again, we subtract, and that leaves us with a remainder, but we don't care about that. This is your asymptote. Okay? All right, let's try number 7. Remember that if your ultimate goal is to graph it, you are going to want to try to factor and reduce before you get started. You can always find your slant asymptote, your end behavior asymptote from the original problem. So you could divide it right now. I'm not going to, because I want to get rid of any holes and stuff before that. But you could set up a division right now and find your end behavior asymptote. You could do that right now. So let's see, how does the top factor? I haven't done it yet, so I don't know. I think it does. Plus 6 minus 2. And then plus 6 plus 1. Vertical asymptote will be where? I'm just filling in his blanks.
How's it plus 6 plus 8?
Did I factor wrong?
No, I'm sorry.
Vertical asymptote at x equals negative 1. Horizontal asymptote, we don't have a horizontal asymptote, but we're going, okay, everybody got that? No horizontal asymptote? How come? The power on top is bigger? What's my slant asymptote? Well, go ahead and find it however you want. You gotta come up with an equation for your slant asymptote. I'm gonna go ahead and do synthetic, because you can do whatever floats your boat. There is no stipulation. I got y equals x minus 3. But I don't know. Is that what you got? Very good. Yep, Avery?
So you don't use the original form of the problem, you just use the simplified one?
It doesn't matter. Now, if you use the original form of the problem, then you will have to do long division, because the original problem has an x squared in the denominator. But no, it's just like if you had some original problem like this, the original looked like that, you could tell right from here that that horizontal asymptote is going to be 1. Well, if you factored and canceled something out, then you would not be looking at x squared over x squared, then you would be looking at x over x. Still, it's at 1. So horizontal or end behavior asymptotes are not dependent on the factoring. Verticals are. Verticals you have to factor, but not horizontals. All right, example 8. Which of the following is correct? what do you think? I went ahead and factored my denominator. What do you think about that? Doesn't it have to be either C or D? Why? Why does it have to be C or D? The power in the numerator is bigger, so we're not gonna have a horizontal asymptote, so we know it can't be anything with that. Now, do we have one hole and one vertical, or do we have no holes and one vertical?
We have a hole. No holes.
We do not have a hole. Why do we not have a hole? We ran into this the other day.
She said that.
Okay?
Because when we cancel them out,
There's still one down there. You guys, you think about this for a second. Where am I? Here. Think about this for a second. If you have a hole and you might think, well, my hole is gonna be at x equals 1, what is the very next thing you do? After you see, oh, I have a cancellation, 1 comma, what's the very next thing you do? Plug in that 1? Can you plug in that 1? No. That means there is no hole. If you cannot plug it in, that means it's a non-removable discontinuity. You can't get rid of it. It's going to be a vertical asymptote. That is why you can't say every time you cancel, you'll have a hole. That's not true. Now, if you have a hole, then you had to have canceled. But sometimes when we cancel, it leaves still a problem, right? All right. Example 9, see if you can put this together. It has to have all the following those. All right, so I'll make a space up here and I need somebody to come up and put a possible picture up here. A possible picture. For example 9. When you think you got it, come on up and show us your version. Remember, there can be more than one. Coal popped in a vertical asymptote at -1. Good idea? Great idea. Because when you approach -1 and you're going either up or down, that means that you're an asymptote. Perfect. Yeah, you're beautiful. So what we've got is, we got some kind of a slant asymptote coming in like that, and the curve is shooting up along that asymptote on this side and down on that side. That's good. The rest of you get something that looks like that? Anybody have a question about his or yours? Yep, okay.
How do you know that there's a slant asymptote?
Well, remember, if your end behavior is shooting out, then you have to be following something as you do that. If you're a rational function, I'm assuming this is a rational function, then it has to have some asymptote that it's following as it leaves the page. Polynomials don't behave that way, but rational functions do. And if we have a vertical in there, we're rational. Okay? All right. For some reason, unknown to anyone associated with this program, we're gonna kind of veer off for a minute and we're gonna talk about binomial expansion, Pascal's triangle, combinations. Any of that sound familiar to you?
Binomial does.
Binomial, good. How about Pascal's triangle? Nope, never heard of it before? Okay, so here's what, I want you just, right now, I don't want you to write anything down, I just want you to sit and listen for a second, kind of watch what's going on. If we took a very simple binomial, like x plus y, and we raised it to the first power, we would just get x plus y, there's no confusion about that. What if we squared it though? What do we get when we square that binomial?
X squared plus yx plus y squared.
Be careful, x squared plus
Yx.
2,
Oh,
2xy or 2yx,
oh yeah.
right? And then if we took it to the third power, that would be like multiplying these two together. And I know because I've done it a billion times, no one would ever memorize this. That would be a tremendous waste of time. That's what you get. Now I'm gonna do one more because you need to make an observation here. I'm gonna make one more. This one I don't have memorized for practicing. I've done it a lot, but I don't have it memorized. And I'm not that smart. There has to be something going on here. There has to be some kind of a pattern. Because we could rattle off x plus y to the 5th, 6th, 7th. We could write them all down without actually doing any multiplication. So what are some observations that you have made from the things that I've done already? Declan?
If you add up the leading coefficients and they're like powers of 2.
Okay, so what he says is, okay, 1 plus 1, I'm looking at just the coefficients. So these add up to 2. 1 and 2 and 1 adds up to 4. And 1 and 3 and 3 and 1 adds up to 8. And 1 and 4 and 6 and 4 and 1 hopefully adds up to 16. Right? Okay, so there's one observation, great. It's a super observation. So I don't know what this x to the 5th or x plus y to the 5th would be, but the coefficients are gonna add up to 32, which by the way, this is 2 to the 4th, this is 2 to the 3rd, so 2 to the 5th, add up to 32, okay, what else?
The x plus 2 adds up to 3, x plus 3 adds up to 4, and then there's 2 plus the 1 adds up to 3,
Okay.
3 plus 3 adds up to
So,
6,
exactly, so
3 plus 1
do you
4.
see what's going on with the letters, variables? 4 and then down to 3 and 2 and 1 and then 0 for the x's. And then the y's, you see that pattern for the variables? Now, he has noticed that the coefficients, if we look at just the coefficients, that they are being generated by adding the two above. So this 3 and 3 is where this 6 came from. And this 4 came from 3 and 1. And that 3 came from 2 and 1 and so on. So the 5th row would start and end with a 1, and then what would go here? 5, 10, 10, 5, and 1. And then could you build the 6th row and the 7th row and so on forever and ever? Sure you could. This is called Pascal's triangle. Blaise Pascal, one of the great mathematicians, actually, like so many of them, he kind of ran with a crowd that maybe wasn't the greatest, and they were gamblers, and they knew he was brilliant, and they said, hey, can you help us win? Smart guy. And so this is kind of the beginning of all that study of probability and game theory and all that stuff. He wasn't doing this with it. Here's what he was doing with it. If you toss a coin one time, there's one chance of getting a head and one chance of getting a tail, right? But if you toss two coins or toss a coin twice, there's one way you could get two heads and one way you could get two tails, and then two ways that you could get one of each. So that's kind of where this all came from. Well, tomorrow we'll pick up here. I need everybody to leave all your things here. And then